Regression analysis is one of the most famous ways to analyze data. If you use the ordinary least square method, the effect is representing a vector of data that you wish to explain as a linear combination of some other data vectors. Now, it is assumed that the vector to be explained is really a linear combination of these other vectors, but we have observed with some error vector. We can think of this error vector as a vector of random variables, and the standard assumptions say that these errors are identically and normally distributed with a mean of 0 and a variance of sigma squared. Whenever we observe the target data vector, the nature rolls the dice to add some errors, but if the nature repeats this many times, we will observe this normal distribution of errors. The coefficients of linear combination that we estimate using the method of least squares from the data at hand are not the real assumed coefficients, but given the assumptions on the errors, they are too normally distributed, with the expected values being the real coefficients and with a certain variance. But then you may ask a question as to why computer software reports the so-called t-values when we test a hypothesis that the specific coefficient is equal to 0. Wait, what are these t-values in the first place? These are the values that we can convert to probability that we observe something as or more extreme as the current data indicate, given the hypothesis that we test, and other assumptions we place are satisfied. Student was a pseudonym of an English statistician, William Gosset, who was worried about making usual statistical inferences in small samples while he worked at the Guinness Brewery and was not allowed to publish under his own name. While it is true that the sampling distribution is normally distributed even in small samples, as long as the population is normally distributed, this stops being true when we also estimate the unknown variance from the same sample. Ronald Fisher subsequently recognized the importance of this work, fixed Gosset's method to correctly use the degree of freedom as opposite to the sample size, and importantly for this video, Fisher applied it in regression analysis. So it is the estimation of sigma squared, the variance that the errors have, that makes us less confident when rejecting a hypothesis on a regression coefficient, that makes the tails of the standard normal distribution thicker, forming a student t-distribution. We can estimate this variance by taking the sum of residuals square divided by the degree of freedom of regression. If we wish to understand the t-distribution, we must first find how the sum of residual squares is distributed. And that is what we will do together in this video. The first thing to do is to establish a connection between errors and residuals. The residual vector is the difference between our data vector y, that we wish to explain, and what we estimated to be the linear combination of the other data vectors. The estimated coefficients of the linear combination b, obtained by the method of least squares, can be expressed with a bit of calculus. Taking y out, we obtain a projection matrix M. M is a projection matrix because it is idempotent. It projects the data vector y into its residuals. In turn, this expression gives us the desired relationship between errors and residuals. At this point, we can try to make an informal argument or a sketch of what we are trying to establish. Since errors are independently normally distributed, also their linear combination is going to be normally distributed. This is not a standard normal distribution, since the variance of errors is assumed constant sigma squared. A sum of squares of residual is then sigma squared times a sum of standard normal distribution squared. In other words, a scaled chi-square distribution. But how many of these standard normal distributions are we squaring? Since there are n residuals, n is our sample size, the first guess will be that there is n of them. But we would be making the same mistake as Gosset did. And as Fisher had explained, we need to find how many of these residuals we are choosing independently. Looking at how the estimator B was derived, we quickly find that the residuals are restricted with a system of equations that has as many independent equations as we have independent variables, including the intercept, in our regression model. In other words, the chi-square distribution has the same degree of freedom as our regression model. Have we then proven that the sum of residuals squared has sigma squared times chi-square distribution with the same degree of freedom as our regression model? If you are convinced, then you can walk away. Nevertheless, I do not believe it. We made several logical jumps, and to turn this into a proof, we need to fill in the details. But if you want to stay, you better get ready for matrix diagonalization. First, we turn our previous observation of residuals being restricted by as many linearly independent equations as there are linearly independent variables into the fact that the rank of the projection matrix M is the degree of freedom of the regression. Since M is a projection matrix, all its eigenvalues are either 1 or 0, otherwise the independence could not be true. By the rank nullity theorem, the number of eigenvalues that are equal to 1 is the degree of freedom of regression, which is the rank of the projection matrix M. By the spectral theorem, notice that M is also a symmetric matrix, we can diagonalize M in an orthonormal basis of eigenvectors corresponding to the two eigenvalues 1 and 0. Because they are orthonormal, inverse and transpose have the same effect. The spectral theorem, as here applied to a real symmetric matrix, is due to Cauchy. Cauchy was the one who made analysis rigorous, and his eigenvalues with matrix diagonalization is an excellent problem-solving tool. If you do not know how to solve a matrix problem, throw in some diagonalization. Now, we are ready to rewrite residuals as a scaled sum of squares. We really have only as many summation terms as is the degree of freedom of regression. When we estimate regression coefficients under standard assumptions and small samples, we need to divide the standard normal distribution by the square root of chi-square distribution, with the degree of freedom being the degree of freedom of regression, which is itself divided by the degree of freedom of regression. Student t distribution is exactly that, and that is why computer software reports t-values. A mystery solved.